Let's now examine public key asymmetric algorithms. Let's start with their operation scheme. There's the plaintext that will be encrypted using a key. This time, the key used for encryption will be called the public key. The output of this operation is the ciphertext. But unlike with symmetric key algorithms, to reverse encryption and to read the ciphertext, a different key will be needed, the private key. Asymmetric cryptography makes use of two different keys. Although they're related to each other, you can't extract either from the other. If you have a public key, you will not be able to generate a corresponding private key. What are the benefits of replacing a shared key scheme with a pair of keys? First of all, exchange is not a problem anymore. The user needs only two keys regardless of the number of other users they want to exchange data with, a private key and a public key. The public key doesn't have, or even shouldn't be, protected. The name is self-explanatory. The key is public and should be shared with all users in a system. A private key, on the other hand, is a user's exclusive property. If it's shared, the entire system is compromised. Secure data exchange in public key cryptography systems with 50 users requires 100 keys, 2 keys per user. Symmetric key systems required as many as 1,225. What's more, asymmetric algorithms allow users to establish a trust relationship. They have one strength that symmetric algorithms lacked: the so-called non-repudiation. You can use this feature to establish the authenticity of a ciphertext. We'll show you how in a moment. And also to prove to a message sender that a message truly comes from them and that its integrity has not been breached. This solution has some shortcomings as well. Public key cryptography is extremely slow. As you've seen, the basic operation used in symmetric ciphers was the exclusive disjunction, XOR. This operation is quick. An equivalent of the XOR in asymmetric cryptography is the modulo operation. The result of modular exponentiation can be a large prime. This operation has a high computational cost. Another weakness is that asymmetric ciphers have not been designed for encrypting long messages. This flows naturally out of the first problem. Several well-documented attacks on asymmetric ciphers have been developed that rely on excessive key use. This situation involves using a key to encrypt messages that are longer than necessary. As a rule, asymmetric encryption should be applied to data that is of similar length to the used key. Keys should be a bit longer than the plaintext. The strength of a 512-bit asymmetric key is more or less equivalent to the strength of a 60-bit symmetric key. As you know, 60 bits does not provide adequate security. 512 bits is likewise insufficient. Today, even a 1024-bit strength can prove not enough unless you're using a modification of the algorithms using elliptic curves. We'll talk about this at greater length later in the module. There are also problems that don't stream from any cryptographic solutions. If asymmetric algorithms allow users to establish trust relationships, you need to keep in mind that ciphers and keys are used by software, not by users themselves. You shouldn't transpose this trust freely. The starting point for asymmetric encryption depends on finding some one-way functions. One-way functions are easy and efficient to compute in one direction, but computationally hard to invert. It's difficult to establish the exact computational complexity of these functions. Whether it's an NP-complete problem or the complexity is simply over-exponential is determined by the development of mathematics. A good example of this is the controversy surrounding the RSA algorithm, which we'll talk about soon. The RSA algorithm's security is based on the fact that multiplying is relatively easy. It's fast. While the decomposition of the object into factors, factorization, has high computational complexity. Just how complex is it? Factoring problems were analyzed by Turing, one of the greatest mathematicians of the 20th century. Turing's paper on factorization remains classified confidential. The UK has been keeping and handling this document as an exclusive possession. What is the reason for this? It could be that, in fact, efficient factoring methods exist after all. I can risk saying this because there's a peculiar correlation. Mathematicians that examine this problem and publish works on factorization tend to disappear from the scientific limelight and scientific life altogether. They are probably working now for agencies that pay better, and beginning from that point, they tend to leave their work or at least don't publish the results. This is relevant since practically all facets of our security depend on the assumed high computational complexity of factorization. Many critically important systems have been based on the RSA algorithm. If a simple laptop would be enough to crack the algorithm, we'd be in a tight spot. RSA is not the only asymmetric algorithm. Algol is just as popular and perhaps even more secure. The two algorithms are designed for encryption and decryption, while the DSA algorithm is used for digital signatures. Algol and DSA are based on a discrete logarithms problem. The logarithm is the inverse operation of exponentiation. The exponentiation can be modular. A modulo is counting to 20 on 10 fingers. The characteristic trait of the modulo operation is that while something is lost, not all information is lost. The same was true for the XOR operation. Since you can perform exponentiation over a modulo, you can calculate a modulo logarithm. As we mentioned, Algol and DSA are based on the computational simplicity of modular exponentiation. This is the logarithmic complexity class. Inverting this operation seems to require a brute force search of all possible exponent values.